Let's understand damped oscillation now. The damped oscillation is whenever oscillation is being obstructed owing to maybe atmosphere or owing to maybe some fluid, we call it as damped oscillation. Alright. Oscillation which has been interfered is damped oscillation. Alright, now let's understand this setup. Now there is the support to which tied a string, to which is tied a block, and to block is tied a vane. This vane is dipped in a container which has got some fluid into it. Alright, and as we have been dealing in case of oscillation, vibration of spring, so we are just pulling it and leaving it. We are just pulling the vane and leaving it, so it keeps on vibrating. Now if it wouldn't have been in fluid, it would have been oscillating freely, but now that the vane is in fluid, so let's understand what happens. Prior to understanding it, let's understand the setup in more detail. Alright, now this is a spring. Now since it's a spring, so it has to have all those properties which we have studied already. That is Fs, the restoring force, which is equal to minus Kx. So Fs is restoring force from spring, and X is the displacement, and it is negative. Why? Because restoring force is in upper direction whereas displacement is in downward direction, so negative. Alright, and K, as we have already seen, is force constant. That's about spring, nothing new about it, which we had already seen in my earlier video. Now let's come to something new. Now this is called as FD, damping force. Now see, as I told you, if this fluid wouldn't have been there, the vane would have oscillated freely. But now since fluid is there, so there are obstructions, there is resistance by fluid. Alright, so let's understand what it is. FD is damping force by medium responsible for decreasing amplitude gradually or for damped harmonic oscillation. Alright, so that is what is FD, property of this. Then V is velocity of vane, velocity of vane, velocity of vane. And negative, why? Because as FD opposes velocity. Alright, this damping force which is there, that's opposing the velocity. Alright, so negative. And B, as we had K, so B is damping constant. So actually this B would depend on the fluid. Higher the viscosity, higher would be B. Like if we have water here, then B, value of B would be less, and if we have honey over here, velocity of B would be very high. Okay, so that's about the setup. Now let's understand the equation. Alright, okay. Force acting on mass at any time t is equal to Fd plus Fs. Fd, it's owing to the fluid over here, and Fs is owing to spring. So restoring force provided by this spring and restoring force provided by the fluid over here. So sum of the two. And we know force is mass into acceleration. So that is this. So this, now we just substitute the values, whatever it has. This value is being substituted over here to get this. Now we also know acceleration is d2x over dt square and velocity is dx over dt. So we just do that, and kx is as it is. So we have taken these on left hand side and we have actually put in terms of d by dx. Alright, so d2x upon dt square plus b into dx by dt. So m is there. Alright, so ma is ma and bv is bv and kx. Alright, is equal to 0. Now on solving, we are not bothered about the solution, but on solving, it's found to be x is equal to ae raised to minus bt upon 2m, where m is mass of the block. All right. Cos omega t plus phi. Now this itself says that it's SHM, and this part which is there, it's a constant. So we have, what I have referred over here is the normal equation that we have for SHM. X is equal to a cos omega t plus phi. So this follows the same pattern. So this becomes the amplitude for our setup. All right. And it's a cos curve. All right. So cos curve. Another thing that I intended to let you know is E is a constant, value of which is 2.718. All right. Therefore, this is the amplitude. That's what I have mentioned over here. Therefore, AE BT over 2M is amplitude of damped harmonic oscillation. See, whenever it's in vibration, damped vibration, if you think of a setup, if you think of this setup, now what we observe normally is that if a simple harmonic motion is given to this system, pulling the vane down and then letting it perform simple harmonic motion, we would find that initially it would be like that, and then it would be going like this. So what did we see? We saw that initially the amplitude was big and time period also was small. Rather, it was moving on very fast. Then we find that the amplitude keeps on decreasing and the time period also keeps on increasing. All right. Let's understand mathematically, does this actually happen? All right. So what I actually told is that initially it would be, see, this is the time period, right? From this is peak of crest. This goes down and then this comes to yet another peak of crest. So T by 4, T by 4, T by 4 and T by 4. That makes one time period. All right. So what we are supposed to check is this distance when it begins and this distance over a period of time. All right. So what we find that here the time period has increased. All right. And another thing that we have got to see is the amplitude. Now, if you see the amplitude, initially the amplitude is more and then the amplitude keeps on decreasing. So that's what I told. Now, if it is vibrating like this initially, so what? The time period is less. So it is moving fast and the amplitude is big. So it's moving fast. And then what is happening is amplitude is becoming small. Amplitude is becoming small and the time period is becoming big. All right. So it is like that. It is bigger amplitude, smaller time period, and now over a period of time gets to smaller amplitude and longer time period. This is what the graph represents. Now let's understand. So that's what I have mentioned over here. Amplitude decreases with time exponentially and the period increases. All right. Okay. Let's try and understand. Now, already derived cos omega t plus phi. So that confirms motion to be SHM. Done. All right, cos curve. So we are seeing it as cos curve. If it would have been a sine curve, then it would have originated from origin, but it is not. All right. So, and omega, on calculation, we derive that omega has this formula: k over m minus b over 2m the whole square all under root. K we know, spring constant, m is mass, and b is damping constant. All right. Now, so time period is 2 pi over omega. So omega thing would go at denominator. All right. 2 pi over omega. So this is the value of omega. Now, mathematically, if value of b is high, denominator, the entire denominator would decrease. Why? If the value of b is high, then we would subtract more from this. So if we subtract more from this, denominator reduces, and if denominator reduces, time period increases. All right. So it all depends upon b, and b depends on what? B depends upon the fluid that we are using. If the fluid has very high viscosity, like say glycerol, like say glycerine or honey, and if it has low viscosity, like say water, then in that case B would be low, and if it is high viscous, B would be high. And we can even visualize actually when highly viscous thing, we will find that you do that instantly it will come back to this state. All right, so time period will keep on increasing. All right, okay, so let's read this out. All right, mathematically, if value of B is high, denominator decreases for the reason that I explained just now. Increasing period of oscillations, slowing down SHM. Higher the viscosity, slower the SHM, as high is B. All right, so that's what is all about the graph. All right, and for amplitude we have to refer this.